Welcome to this educational video on heat transfer through materials with variable thermal conductivity. Today we'll analyze a one-dimensional heat conduction problem through a solid slab with variable thermal conductivity and visualize the resulting temperature distribution. Let's begin by understanding our problem. We have a solid slab with thickness L. The thermal conductivity K of this material varies with the spatial coordinate x, according to the equation K equals a plus B times x, where A and B are positive constants. The slab has fixed temperature boundary conditions. 0 temperature at x equals 0 and temperature T subscript 0 at x equals L. Our goal is to determine the steady-state temperature distribution within the slab, considering one-dimensional heat transfer with no internal heat sources. Let's start with the governing equation for our problem. For steady-state, one-dimensional heat conduction with no internal heat generation, Fourier's law gives us the derivative with respect to x of k times dt/dx equals 0. Substituting our variable thermal conductivity k equals a plus bx, we get the derivative with respect to x of the quantity, a plus bx times dt/dx equals 0. Now, let's solve this differential equation step by step. First, we integrate the equation once with respect to x. Since the derivative equals 0, the expression inside must be a constant. Let's call this constant c sub 1. Rearranging, we get dt/dx equals c sub 1 divided by a plus bx. To find the temperature function t of x, we need to integrate again. We have the integral of dt equals c sub 1 times the integral of dx over a plus bx. The integral of dx over a plus bx gives us 1 over b times the natural logarithm of a plus bx. So, t of x equals c sub 1 over b times the natural logarithm of a plus bx plus another integration constant c sub 2. Now, we need to apply our boundary conditions to find the constants c sub 1 and c sub 2. First, at x equals 0, t equals 0. Substituting, we get 0 equals c sub 1 over b times natural logarithm of a plus c sub 2. Solving for c sub 2, c sub 2 equals negative c sub 1 over b times natural logarithm of a. Next, at x equals L, t equals t subscript 0. Substituting and also using our expression for c sub 2, t subscript 0 equals c sub 1 over b times natural logarithm of a plus bl minus c sub 1 over b times natural logarithm of a. This simplifies to t subscript 0 equals c sub 1 over b times natural logarithm of the ratio, a plus bl, over a. Now we can solve for the constant c sub 1. C sub 1 equals b times t subscript 0, divided by the natural logarithm of the ratio, a plus bl, over a. Substituting both constants back into our original temperature function, we get the final solution. T of x equals t subscript 0 times natural logarithm of a plus bx over a divided by natural logarithm of a plus bl over a. Now, let's visualize and analyze the temperature distribution within the slab. Here's a plot of the temperature profile T of x from x equals 0 to x equals L. Looking at this temperature profile, we can observe several important characteristics. First, the temperature increases monotonically from 0 at x equals 0 to T subscript 0 at x equals L, which aligns with our boundary conditions. Second, the curve is concave downward. This means the temperature rises quickly near the x equals 0 boundary, and then the rate of increase decreases as we move toward x equals L. This shape is a direct consequence of the increasing thermal conductivity. As x increases, the thermal conductivity K also increases, meaning the material becomes better at conducting heat. In regions of higher conductivity, the temperature gradient is smaller because heat flows more easily. Physically, this means that the temperature changes rapidly in low conductivity regions and changes more gradually in high conductivity regions, which is exactly what we observe in our solution. To summarize what we've learned, we've solved the one-dimensional heat conduction problem for a slab with linearly varying thermal conductivity. The temperature distribution follows a logarithmic function, which is concave downward. This analysis is important in many engineering applications where materials have variable properties, such as composite materials, functionally graded materials, or materials under varying temperature conditions. The key insight is that in regions of higher thermal conductivity, the temperature gradient is smaller, leading to a more uniform temperature distribution in those areas. Thank you for watching this explanation of heat transfer in materials with variable thermal conductivity.